Hello, welcome to video lecture number 5 on strength of materials.
We were discussing about the stress strain diagram, a very important concept in mechanical engineering. We have seen a typical mild steel specimen. You can see that tensile specimen will look like this. You can see its red markings here. Between those markings, the deformation is measured, and that distance initially it is called gauge length, and diameter of the specimen is taken as d0. So specimen will always be like this for tension test. UTM, universal testing machine, can be used for compression test also. So if you want to do the test for compression, you have to use a specimen of this kind. So it will be a simple cylinder, because for compression you don't have to hold the specimen, you just have to press using two shackles. So now to plot the stress strain diagram, we have seen when we increase the load, corresponding deformation also will increase, and initial portion of the stress strain curve will be a straight line, because Hooke's law will be valid there. So initially it will be a straight line like this, and beyond certain point it deviates from the linear relationship and it reaches upper yield point. Then it slowly comes down, and again at this point, at lower yield point, it again increases to a maximum value, and if you continue to load, it goes down little and it fractures here. This is the fracture point, this is the ultimate stress point, this is the lower yield point, this is the upper yield point, and there will be two more points here. One is called elastic limit and other one is called proportionality limit. This region is called elastic region. Beyond that, till the fracture, it is called plastic region. This is a yield region. This region is the strain hardening region. This region we called it as necking region. And slope of this straight line, if you take, it will be Young's modulus. Strain hardening, this is stress and strain. And let us say I am loading the specimen. Initially it will be a straight line like this, and it reaches upper yield point, lower yield point, and it starts increasing from here. If I stop loading here and reverse the loading or remove the loading, it will go back like this. So this is the forward path, this is the loading path, and this is unloading path. If I unload the specimen at this point, before it reaches ultimate stress, it comes back like this, and this will also be a straight line, and it comes to zero stress at this point. And if you see, even at no load, this much is a strain that is present in the material. This is called plastic strain. So this much permanent strain is observed in the material when you unload the specimen completely. And if you reload it, it will take the same path now. It will start from here now, and it will go like this. And now you see that till this point, stress will be proportional to strain. So previously it was only till here. Now it has increased. So the material capacity has increased by this much. So the new yield point is more than the original yield point. In other words, you can say that material is hardened. Right? That is why this region is called strain hardening. Stress strain curve for high strength steel. The initial part will be a straight line like this, and beyond certain point it continues, but slowly it comes like this and it fails somewhere here. So if you observe this kind of plot, you will not see, or you will not be able to differentiate the yield point. In the previous case, if I draw a dotted line here, this is called yield stress sigma y. That is the yield stress of the material. But here, in case of high strength steel, you will not see such point. You will not be able to define the yield stress in a clear cut point. This type of material behavior is observed in brittle materials like high carbon steel, cast iron, and so on. For such materials, in order to have a theoretical value of yield stress for analytical purposes, there is a method called offset method. If you use offset method, you can define a theoretical yield stress, which is also called as proof stress. How it is obtained is, on the x-axis, 0.1% or 0.2% strain is taken. Along strain axis, I am measuring 0.1% or 0.2% strain. After measuring this 0.1% or 0.2% strain, there a straight line is drawn from that point. So from this point, I am drawing a line parallel to the initially drawn line, and that straight line, you observe, it is crossing or it is intersecting stress strain curve at this point. Corresponding stress, if you measure on the y-axis, this stress, whatever you get here, this is used as the stress which is equivalent to yield stress. So this particular stress is called sigma P or proof stress. Sigma P at which if the loading is made, there will be 0.2% permanent deformation, and that is known as proof stress. And this point is treated as yield point for all practical purposes, or you can define the proof stress as a stress necessary to cause a non-proportional or permanent extension equal to a defined percentage. Normally it will be 0.2. See, 0.1% strain is nothing but zero point 0.1 divided by 100. So it is 0.001. So 0.001 strain you have to take here on x-axis. If you measure sigma P at 0.1% strain, it is called as yield stress at 0.1% offset. If you measure it for 0.2% strain, then it is called sigma P at 0.2% strain. True stress strain diagram. Say the specimen diameter you have taken as D0 and you have taken the length as L0 for tension test. When you load this specimen, let us say you load it at 10 kilonewton. So when you load it to 10 kilonewton, the diameter D0 is changed
And length also will be changed.
Next, when you increase it to 20 kilonewton, if you want to calculate the stress now, you have to take the changed diameter, or strain should be calculated based on the changed length. So at every point increase the load, dimension of the specimen is changing. Dynamically it will change. But what we have done in the previous case, we calculated sigma as P by A and epsilon as dl by L. And which value of A we have taken for all the calculations? It is the original dimension. And for all the strain calculations, we have used original length. All the calculations we have done like this only. So stress and strain, whatever we have obtained, that is called engineering stress strain, or it is also called conventional stress or strain. Instead of original area and original length, if you use what is the area at that instant or what is the length at that instant, we will get a different stress and strain values. Instead of original area, original length, at any load point, if I use the instantaneous means at that instant, what is the area, what is the length, that if I use, I will get a different stress strain values. Those stress strain values are called true stress strain values. So stress or strain evaluated based on original dimensions is called conventional or engineering strain or stress, and stress strain evaluated based on instantaneous dimensions is called true stress or true strain. So how does it look like? We know how a conventional stress strain diagram look like for mild steel. Initially it will be a straight line like this, then it slightly deviates and it goes like this, it becomes ultimate stress and it fails here. So this is a conventional stress strain diagram, and we can locate upper yield point, lower yield point, ultimate stress point. So I'll just call them as A, B, C, D. This is conventional stress strain diagram. Okay, now if I take instantaneous cross section and try to draw the stress strain diagram, it looks like this. This point is corresponding to the fracture point. This point is corresponding to the ultimate stress point, and a point you can note here as the lower end. So corresponding points are shifted above when you use true stress strain curve. So this is true stress strain curve. If somebody asks you what is true stress, you have to define it as the ratio between the load at any instant and the cross-sectional area over which the load acts at that instant. That is the true stress definition. And true strain, if you want to define, it is the ratio of change in gauge length and the instantaneous gauge length. Factor of safety. I will just give you an example. Let us take an example of a table. This is manufactured by some company, let us say company A. He will give you a specification that a person with a weight of 100 kg can sit on this. This is a specification he gives. As a manufacturer, company A gives a specification that the maximum load the chair can take is 100 kg. Let us say while using it, you have loaded it at 110 kg. Do you think it is going to break? company makes use of something called factor of safety. And based on his design, he has calculated at what load this chair is going to fail. Maybe at 150 kg, it is going to fracture. He would have tested it in the laboratory. So this is the failure load, and to keep the user's safety or many other parameters, he will suggest that safe load can be 100 kg. So there is some factor that is playing here, and that is called factor of safety. Now the factor of safety for this chair case is 150 by 100. So 1.5 is the factor of safety. One more example. You would have seen in lifts, they will write maximum 8%. The manufacturer will give you a limitation like this. So it does not mean that if 9 people go, lift is going to fail. It may not fail. But manufacturer has tested the lift. It would have worked for maybe 12 persons also. But if you go to some particular weight, maybe 13%, it fails. So as a safety measure, he suggests the user to use only 8%, or sometimes he will tell you maximum 900 kg. Failure load can be maybe 1500 kg. So he is keeping some factor of safety and giving you the allowable operating condition. So factor of safety can be defined as the amount by which the design stress or design load is kept below the limiting value. In terms of stress, the limiting value is yield stress. If you observe the stress strain diagram, at the yield stress, more plastic deformation is observed. So whenever we use a component, we don't want the component to yield. Once it starts yielding, it is a failure for us. It need not have to break. So the yield stress itself is the limiting stress. But some materials, we will not see the clear-cut yield point. So for such materials, we will also use ultimate stress. So if it is a ductile material, you will clearly see the yield stress. If the material is brittle, then ultimate stress is used as a limiting stress. Mathematically, we can write FOS as yield stress divided by allowable or design or working stress. If it is brittle material, instead of yield stress, you will be using ultimate stress. So this is the definition of factor of safety. And this factor of safety accounts for so many uncertainties. So what are those uncertainties accounted for factor of safety? We'll make a list now. So factor of safety, FOS, accounts for first one, unexpected loads. Unexpected load means if the chair is designed for certain value, maybe 100 kg, if suddenly unknowingly some extra load is added, that will be accounted in terms of factor of safety. Second, manufacturing defects. Third point is environmental effects. It accounts for effect of size, shape, type of loading. It accounts for wear. So all these parameters will be accounted in terms of factor of safety. Now, how much factor of safety is kept for normal design? There is no hardcore rule to use the specific factor of safety, but in general, for aerospace applications, a factor of safety of 1.25 to 1.5 is used. For medical equipments, factor of safety of 10 or more than 10 is used because their human safety is very important. And in aerospace also it is important, but their precise design will be made. And if you keep very high factor of safety, the material cost will be increased, so overall cost also will increase. So they try to keep optimum factor of safety in case of aerospace applications. And in other applications, maybe factor of safety of 2 to 5 is kept. Again, it depends on the application, type of loading, and so many other factors.